أعوذ بالله من الشيطان الرجيم. بسم الله الرحمن الرحيم، والصلاة والسلام على أشرف خلق الله المرسلين سيدنا محمد وعلى آله وصحبه وسلم. ما زلنا في سلسلة نظريات نموذج المعيار والتفاعلات المادية، وهذه الحلقة 25 تتحدث عن تكميم معادلة يكمل. لكن أيضا أريد أن أعلمكم بآخر التطورات في كتاب الحلقة 55. أنا طبعا في هذا الكتاب الحمد لله انتهيت من الحلقة السابقة ووضعت فيه تصوراتي، عملت معي 8 صفحات، وحاولت أن أشرح ما توصل إلى المحاضر في الحلقة السابقة من خلال نظريتي أنا، من خلال كتابي الحلقة 54. فتوصلت إلى يعني نتائج مرضية، و يعني حبست أنني لا أختم على هذا وأنشر مباشرة حتى أصل إلى التكميم لمعادلة يكمل وكتابة اللاجرانج النهائي، ولا أصل إلى فاينل رولز. وبعد ذلك سأحاول أن نضع هذه المفاهيم الجديدة إن شاء الله في كتابي، وأحاول أفسرها على ضوء ما ذهبت فيه في بداية الكتاب. وطبعا من أهم من الأهميات القصوى أو الشيء الأساسي لأي نظرية يجب أن تكون تسمى بسلف كونسيستنس، يعني تكون ليست متناقضة في ذاتها. فلهذا الأمر، بسبب هذا الأمر هذه الحلقة مهمة. الحلقات اليوم هي مهمة، لأنه إذا تناقضت كتابي مع حلقة اليوم، إذا تناقض فهذا يعني أنه هناك مشكلة في الكتاب. فحلقة اليوم هي مهمة، وبسببها أنا أجلت نشر الكتاب أو أختم والديكور وكل ذلك في الكتاب. لم أعمل الديكور ولم أختم حتى الآن. سأنظر إلى حلقة اليوم وإن شاء الله وأحاول أن أنزلها ربما كشابتر مختلف، شابتر الثاني. وإذا كانت معلومات الفيها ليست كثيرة سأنزلها في شكل سيكشنز وأفكر في النشر، وبعد ذلك أختم وأنشر بإذن الله تعالى. طيب، فلنبدأ إلى الحلقة 25.
Okay, let us start with today's lecture in Quantum Field Theory 2. Last time we have started with a new chapter, namely Yang-Mills theories, and we gave a short motivation, discussed the building blocks, and in the end we wrote down the Lagrangian. And today we will talk about problems and strategies for the quantization of Yang-Mills theories. So basically, as you know, gauge invariance means there is a first class constraint. So it basically means that we have unphysical degrees of freedom whose time evolution is undetermined. And furthermore, we have that there is no canonical conjugated momentum for A0. And we have also problems with defining the path integral. So let me first write down some of the problems. So this is chapter 2.2. Problems and strategies for quantization. And start with the problems that I've just mentioned. So as I said, gauge invariance is the first class constraint, as you know from quantum field theory 1b. We have no canonical conjugated momentum for A0. which is that pi 0 is identically vanishes. And as I've said, the path integral is undefined because we're integrating over infinitely many physically equivalent gauge configurations. So path integral over infinitely many. So as you know, in the path integral, we always integrate over all possible field configurations. And here, we are integrating over infinitely many physically equivalent gauge field configurations with the same value of the action, which means that the path integral is divergent. So, and the standard procedures are that we, if we have already seen it, for instance, for QED, we make a gauge fixing, then we canonically quantize it, and then go translate this to the path integral. So let me start with the standard procedures. Make a gauge fixing, canonical quantization, and translate to path integral. For instance, you can have a look at Weinberg, chapter 15.4. There is a different approach, which is the so-called Faddeev-Popov approach, which you might have already heard. So basically in the Faddeev-Popov approach, as I've said, we are integrating over infinitely many physically equivalent gauge field configurations. So we want to integrate in the Faddeev-Popov approach. We want to integrate only over one representative for each gauge orbit. So we have to introduce, in order to kind of divide the other equivalent gauge configurations out of the path integral, we have to introduce the Faddeev-Popov determinant, and can write this using fermionic path integrals in terms of these path integrals with Grassmann-Maillout fields. And we then identified these Grassmann-Maillout fields as so-called Faddeev-Popov ghosts. And I will just teaser this method because we will not discuss it here. We will do something else. We will do the BRST formalism. But if you come from the Faddeev-Popov approach, you basically discover the BRST formalism. So let me just write a short comment on this. Faddeev-Popov. Path integral construction. Where we only integrate over one representative of each gauge orbit. And basically here we can discover BRST symmetry. However, as I've said, here we will immediately start with the BRST formalism. So, and as Dominic already said, here we will only do perturbative quantization. If you would like to have a look at some non-perturbative issues with respect to the quantization of non-abelian gauge theories, you can have a look at either of these two papers. This is by Sorella, and the other is by Dudal and others. And if you would like to have a look at, for instance, the Faddeev-Popov path-integral construction, you can have a look in Peskin-Schröder, the Schwarz book about quantum field theory, and I think also in Weinberg. There are several chapters about it. So, and basically what we want to do with the BRST formalism is that we would like to, so we have our classical theory with gauge invariance and our constraints, and we would now like to get a new theory which is physically equivalent and with a new symmetry, namely the BRST symmetry, and we can then basically see the BRST formalism as a complete and proper substitution for gauge invariance. And let me just teaser some of the results that we will encounter, and then we will directly dive into the BRST formalism. As I said, new physically equivalent classical theory with new symmetry, namely BRST symmetry. We have a gauge fixing. We will have the Faddeev-Popov ghosts that I have already mentioned. And as I said, BRST invariance. The theory is quantizable, so quantization is possible. So what do I mean with that is basically that the Lagrangian that we obtain from the BRST formalism is of the form that we discussed in chapter 1 when we discussed the path integral quantization. So it is it has second order constraints and also contains unphysical fields, for instance this an auxiliary field, which is however at most quadratic in the Lagrangian. So it is exactly of the form that we allowed for the path integral quantization. And in this sense, it is the theory is quantizable using the path integral formalism. And we encounter an operator, namely the BRST operator. BRST invariance provides an operator Q which is self-adjoint. It is nilpotent, so means that it anti-commutes with itself which means that it is a fermionic operator, and it commutes with the physical S matrix. And so now that I gave you a first introduction to what we will be doing this lecture, but also the next weeks, let me start by introducing the BRST formalism. And we will start with the ideas of the formalism. So as I've already said, we will replace our classical theory with a physically equivalent theory, but which is quantizable. So let me write that down once more. Replace classical theory with new physically equivalent one that can be quantized. And we will identify physical states with equivalence classes. And please recall from quantum field theory 1b, the Gupta-Bloiler approach, where we had something like H physical, which is our physical Hilbert space, which was defined as the quotient space of V physical by Vs. And Dominic already wrote that down in the motivation last week. So what we are now doing is similar or like Gupta-Bloiler, but more systematic. So let me start by first so basically, what do I mean with equivalence classes? And we say that a physical state psi and the state psi prime are physically equivalent if they sit in the same equivalence class. So let me just formally write that down. Psi is physically equivalent to psi prime if psi prime equals psi plus BRST operator acting on some chi. And first, this chi is arbitrary. And this is basically like a gauge transformation. And the equivalence class is given by and this basically tells us that gauge transformations do not change physics. So then the second thing that we need to clarify is what do we mean by physical, or more precise, what means that psi is a representative of the physical equivalence class. So second, psi is, and I will write that down in quotation marks, physical, because here we have to be careful. I will also specify this more. This psi, which I am now writing down, is a representative of the equivalence, the physical equivalence class, and lies in the kernel of Q, which is this V physical. But the actual physical states are elements of this quotient space, namely in H physical. I will specify this also further later, but let me just write that down in order to be consistent also with our notations from quantum field theory 1b. And so we call it in some sense physical if the state psi is annihilated by the BRST operator. This is basically something like gauge invariance. And here I will write that down. Psi is a representative of the physical equivalence class. Which means that psi is an element of V physical, which is the kernel of Q. Please recall, I will also write it down later. The kernel of Q is basically what is annihilated by Q. And so, and recall that if we have a state that is of Q, it is, as you might recall from quantum field theory 1b, representative of the equivalence class of the zero vector. So, but yes, so far so good. Let us come to 3, namely consistency. And what do I mean by consistency is that the BRST operator is nilpotent and self-adjoint. And in this case, equivalent states are all physical, or either all physical or all unphysical. And if we consider the scalar product of two physical states, which we might want to do in quantum mechanics, it is independent of the representative of the equivalence class, which it should be. Independent of the representative of the equivalence class, at least for physical psi and phi. And in the time when I will clean the blackboard, you have some time to think, or maybe also prove as some kind of a task that this scalar product is indeed independent of the physical, of the representative of the equivalence class. So please feel free to do that while I am cleaning the blackboard. So, in other words, from physical equivalence classes, we obtain our physical states, and we can now properly define our physical Hilbert space. H physical is defined as the kernel of Q as the quotient space of kernel of Q by image of Q. So let me be more precise what I mean by, I think you all know what the kernel of Q means, but the kernel of Q are all those states which are annihilated by Q. And the image of Q are all those states which can be written as a Q exact state, or in other words, as a total Q variation. So in other words, we call this BRST closed states, and this BRST exact states. And this terminology might be familiar to you. So sometimes this is called the BRST cohomology, and we then say that our physical states lie in the BRST cohomology, which is the quotient space of the closed states and the exact states. And this is our physical Hilbert space, and it contains the space, our physical states. So it's the space of physical states. Due to the fact that the operator Q, so first of all, every exact state is necessarily a closed state, as you can see from nilpotency. If we have an exact state, we can write it as a total Q variation. And if we then act with Q on this state, it's of course 0. So every exact state is necessarily closed. However, the converse is not necessarily true. And this is basically then what we make use of, and that's also why we call it the BRST cohomology. And also, due to the fact that Q is nilpotent, the image of Q entirely lies within the kernel of Q. And let me write down some remarks with respect to this. So, as I said, every exact state, or let me write it in words. Every exact state is necessarily also closed. However, the converse is not necessarily true due to nilpotency. The image of Q lies entirely within the kernel of Q. The true Lagrangian is is element of the kernel of Q, but not in the image of Q. And that means in our terminology that it lies in the BRST cohomology, which is necessary because, as I said, H physical is the space of physical states, and our true Lagrangian is our physical Lagrangian. So true Lagrangian is in kernel of Q, but not in the image of Q. Our V physical, which we had in the Gupta-Bloiler approach last year in QFT1b, is, as I've already mentioned, the kernel of Q, and is in some sense the space of gauge invariant states. Our Hilbert space is H physical. It consists of our physical states, and our physical states are basically BRST closed states modulo BRST exact states. And yeah, let me write that down. H physical is the Hilbert space physical states, which means it consists of BRST closed states modulo BRST exact states, and we say physical states lie within the BRST cohomology. So let me write that down. Okay, what we can further show, but we won't do it in this lecture, is that H physical is a positive definite Hilbert space. Positive definite Hilbert space. And that the S matrix on H physical is unitary, gauge fixing independent, and does not lead out of the physical Hilbert space H physical. S matrix on H physical is unitary, gauge fixing independent, and does not lead out of H physical. Does not lead out of H physical. In summary, we might now say that this gives us a meaningful theory for spin 1 particles, and our goal is basically to find a theory such that a Q, an operator Q, exists which has these properties. So physical meaningful theory for spin 1 particles. And our goal is to define a theory such that there exists an operator Q with these properties. So we will now come to the BRST transformations, which basically then substitute our gauge transformations. But let me clean the blackboard first. So BRST transformations let me maybe now comment on why it is called BRST. So these are basically just the names of the physicists who discovered it. Becky, Goel, Storer, and Tutin. In 1974. But so far so good. What we want to do is on the classical level, we want to go from our gauge transformations to BRST transformations. And in order to get infinitesimal transformations, we need an operator S. And then after quantization, we get a corresponding Noether charge, and this Noether charge will be identified to be our Q operator, which is the BRST operator. So classical level. Gauge transformations would like to get BRST transformations. For infinitesimal transformations, we need an operator which I will be calling S, and then after quantization we obtain a Noether charge which will be identified to be the BRST operator Q. The idea.
طبعا هنا أريد أن أقول كلاما هو أن السبب الذي جعل معادلة ياغميل تذهب بمذهب BRST formalism والتي تعتنق equivalent classes ناتج من الأشياء هي طبعا أولا علينا نعرف معادلة ياغميل تصف الكيو دي وقد تصف الكيو سي دي، وذكرت في فيديو سابق اللي هو الفيديو عن لماذا التمرد الويك فورس أو لماذا الويك فورس تخرب الفيزياء. هذا الفيديو ذكرت فيه أن الانتقال من أبعاد كبيرة اللي هي أبعاد البروتون إلى أبعاد صغيرة اللي هو 10 أس 18 تمر بانقلاب. هذا الانقلاب انقلاب في الأبعاد. تعالوا نشوف المعادلة. هذه المعادلة التي تخبرنا بذلك. طبعا ضمنتها في كتابي، الآن أنا بصدد الانتهاء منه ونشره إن شاء الله. نجد أن الحد الأول يمثل حد ذو أبعاد كبيرة، وإن كانت داخل البروتون لكن أبعاد كبيرة داخل البروتون، فيمثل بالحد الأول. الحد الثاني اللي هو ناقص 2 GM على C⁻R، هذا لا يظهر إلا بعد أفق الحدث. والبروتون إذا فرضنا أن البروتون هو ثقب أسود، فإن أفق حدثه لا يكون إلا داخله إذا أبعاد بعيدة، يعني عند أبعاد 10 أس ناقص 20 أو 18 19، هذه الأبعاد. وكما ذكرت أن كتلة البروتون عالية في تلك الأبعاد، كتلة البروتون عالية. فالسبب الأساسي الذي جعل العلماء PRST ذكرهم المحاضر الآن أن يؤلفوا وأن يدخل في نموذج الإيكوفالنت كلاسز وهذه المعادلة، والذي تخبرنا بأشياء. هي أولا أنه كتلة البروتون ليس كما نراه. طبعا الشيء الأساسي في الإيكوفالنت كلاس هو محاكاة للنسق العام، لكن هو ليس نسق عام. النسق العام معروف أنك canonical quantization أو الفايمان باس انتجرال كوانتيزيشن، معروف شرحناه في هذه السلسلة، واستمعنا المحاضر شرحه بكل أريحية. فهذا هو النسق العام. لكن إنك تلجأ من أجل الجيج فيكسينج، تلجأ إلى الإيكوفالنت كلاسز، هذا يعني أن هنالك شيء تراه ليس حقيقيا. طبعا هو حقيقيا، أنا شرحت ذلك أن الإيكوفالنت كلاسز هي حقيقة، لكن نحن بالنسبة لنا كملاحظين خارجين نراها ليس حقيقة، لأنه لدينا فهمنا الخاص. نحن نرى كتلة البروتون لا تتغير. ما الذي يجعلها من 10 أس ناقص 28 تذهب إلى 10 أس 10؟ طبعا تعتمد على المرجع الملاحظ، ونحن ليس لدينا التكنولوجيا الكافية أنه نستطيع أن نكون ملاحظين عن قرب لهذا البروتون. إذن كتلة البروتون هي سبب من الأسباب اللجوء إلى الإيكوفالنت كلاس. السبب الثاني هو عند الأبعاد الصغيرة البروتون يتحول لثقب أسود أو يقترب من الثقب الأسود، وبالتالي يقوى أو يشتد الحد الثاني. الحد الثاني هو الحد المشهور الذي يسمى بحد شوارشالت، وهو الحد المشهور الذي يعطينا فضاء داخل الثقب الأسود. فهذه المعادلة، معادلة يانغ ميل، التي تفسر QSCD والQED وربما EW، إذا أردناها أن تكون بهذه الهيئة لابد أن نرجع للإيكوفالنت كلاس. وربما يتم صياغات مختلفة، نفس المعادلة لكن يتم صياغات مختلفة بين الQCD والEW. وأعتقد ذلك، أعتقد أنه إذا دخلنا إذا المحاضر يعني تحدث عن الQCD بعمق ويتحدث عن الEW، ربما سنجد هذه الاختلافات، أنه يجب أن نصحح بعض المفاهيم ونبتكر بعض المفاهيم، لأن نحن في الإيكوفالنت كلاس، والإيكوفالنت كلاس يعطينا فيزيكال ريزلت، لكن الحقيقة هو ليس فيزيكال فاكت. فقط نعتمد اوبريتور يعمل انهيليشن لستيت ويعطينا زيرو، وبعض الخصائص التي ذكرت في الإيكوفالنت كلاس، لكن هو ليس فيزيكال، هو ليس فيزيكال فاكت، ليس واقعنا، هذا ليس واقعنا، لكنه لديه بعض الخصائص الفيزيكال. فعند الانتقال من الQCD إلى الإلكترويك لابد لنا في معادلة يانغ ميل لابد لنا أن نعدل بعض المفاهيم ونضيف بعض المتغيرات. هذه المتغيرات سنجدها إن شاء الله إذا تطرق عليها المحاضر سنجدها مباشرة تفسرها هذه المعادلة مباشرة، لأن هذه المعادلة هو جزء من الفضاء، جزء من الفضاء. هذا الفضاء هو جزء من الفضاء، هذا الفضاء هو فضاء مترية على اليوسف. هذا الفضاء هي شبيه بفضاء مينكوسكي وشبيه بفضاء شوارزشيلد، لكن هذا الفضاء لديه اختلاف عنهما في ماذا؟ أن الحدود مثلا فضاء مينكوسكي نجد البري فاكتور بالنسبة للدي تي اللي هو تغير محور الزمن، والدي ار محور المسافة. البري فاكتور عبارة عن واحد اللي هو ايتا تاخد 1-1-1-1 أو تاخد -1-1-1 حسب السيجنتشر. يعني نجد أن معادلة مينكوسكي جامدة خصوصا في البيري فاكتور، فهي عبارة عن واحد. معادلة شوارزشيلد هي أقل جمودا من مينكوسكي، وتأخذ 1-2 على سي². هذه هي معادلة شوارزشيلد، تأخذ 1-2 على سي². إذن تبدأ من حدود مينكوسكي ونحن داخلون على الثقب الأسود، يتحكم الحد الثاني اللي هو 2 على سي². وبالتالي تحكم هذا الحد يخبرنا ماذا يوجد داخل الثقب الأسود، لكن خرج الثقب الأسود يبدأ بمينكوسكي مباشرة، يبدأ بمينكوسكي اللي هو الواحد. معادلتي لا تبدأ بمينكوسكي، تبدأ ما هو بعد مينكوسكي وهو ألفا. ليس واحدا، ألفا هذا هو الرقم لألفا يتغير من 81 إلى 0. انظر الواحد موجود وين؟ الواحد موجود أمام هناك، لكن بعد الواحد في الدالة اللوغاريتمية. الدالة اللوغاريتمية داخلها سرعة الضوء 6 على 16 ثابت نيوتن تربيع كتلة تربيع. فمع صغر الكتلة هذه المعادلة تعطينا رقم أكبر من الواحد، وهذا ما يعطينا ما بعد مينكوسكي. يعني مثلا نضرب مثل أن لدينا الفضاء، لدينا ثقب أسود، تمام. مينكوسكي يخبرنا فضاء قريب من الثقب الأسود ماذا يحدث. قريب ليس بالقرب الكافي حتى تتأثر الجاذبية، لكن قريب. اسمه شوارزشيلد يعطينا انتقال من الفضاء القريب إلى الفضاء داخل الثقب الأسود مرورا بأفق الحدث. معادلتي تعطينا فضاء بعيد جدا جدا من الثقب الأسود، بعيد أبعد ما يكون من الثقب الأسود، اللي هي تظهر فيه خصائص المادة المظلمة والطاقة المظلمة وما إلى ذلك، ونحن ذاهبون إلى فضاء مينكوسكي ثم ذاهبون حتى فضاء شوارزشيلد. هذا هو الفرق. هذا الفضاء يطبق في البروتون بالمناسبة، يطبق في البروتون. يعني أنت بس فقط في هذه المعادلة تعوض كتلة البروتون، لا تجعلها ثابتة، تبدأ من 10⁻⁸ وأنت تزيد فيها، تزيد مع نقصان نصف القطر. نصف القطر طبعا يعتبر المسافة، مسافة الملاحظ، تزيد مع نصف القطر، تزيد حتى تدخل مرحلة الثقب الأسود اللي هو -2 على سي². هذه مرحلة داخل الثقب الأسود. عند هذه المرحلة نحن نقف، لأنه الثقب الأسود آخر مرحلة يسمح لها فضاء ثنائي الأبعاد. بعد هذه المرحلة فضاء ثنائي الأبعاد سيحارب حتى داخل الثقب الأسود، سيحارب زيادة بدرجة كبيرة في الثقب الأسود. فإذا سنصل الثقب الأسود ونقف ونحسب التغيرات التي تحصل في الفضاء. هذا ما يحصل هذا ما يحدث. فالإيكويفالنت كلاسز هو سببه عدم مقدرتنا إلى هذا الانتقال، وعدم معرفتنا بالبيئة الداخلية للبروتون والنيوترون، كواركات، ليبتونات. فهذا لجأنا للإيكويفالنت كلاس، لكن إذا عرفنا ذلك يمكن أن نستغنى عن الإيكويفالنت كلاس. وشيء أساسي من معرفتنا أننا الكتلة ليست ثابتة والطاقة ليست ثابتة، فداخل التفاعلات أو داخل البروتون إلى حد ما الطاقة تتضخم ثم تقل عند الدخول الثقب الأسود، طاقات تقل، كتل تقل عند دخول حدود الثقب الأسود. لكن دعونا نقف عند الحدود لأنه الفضاء ثنائي الأبعاد يمنع ذلك، فنجد أن الطاقة تزيد والكتلة تقل. الفضاء الكثيف الكتلة ذات نفسها تقل لكن الطاقة تزيد. هذا الكسر في التناظر لا يعلم، لا يمكن الفيزياء أن تقبله، لهذا لجأوا العلماء للإيكويفالنت كلاس. سأدون هذا في كتاب إن شاء الله الذي بصدد إخراجه، وإن شاء الله سأحاول أن أقدم فهم عميق للفورماليزم الجوبتا بويلر، فورماليزم للجيج فيكسين الذي يعني عملوه في السبين 1 بارتيكلز، خصوصا السبين 0 أقصد الماسلس. وإن شاء الله سأدون ذلك في كتابي بإذن الله تعالى. طيب نرجع للمحاضرة.
Is that S generates symmetry transformations, is a fermionic operator, is nilpotent, changes the so-called ghost number by +1, and does not change the power counting dimension. So let me all write that down. So first, S generates a symmetry transformation of the form some field phi goes to phi plus lambda S phi, where this lambda is a fermionic parameter or so-called Grassmann number, so it anti-commutes. Let me write that down. Fermionic parameter. S itself is or acts as a fermionic differential operator. So what do I mean by this? How can we understand this? Basically, if S acts on F1, F2, B1, ... So we have some kind of a string here of different objects, a fermionic object, another fermionic object, F2, and a bosonic object, B1, and several other objects. The action of S on this is, as you might note from a differential operator, however, it is fermionic, so it anti-commutes, which means it first acts on F1 and on nothing else, F2, B1, ... and then it acts on F2. However, acting on F2 means we have to anti-commute it past F1, so we have to pull it past F1, which means that we get a minus sign. So we don't have, as you usually have for the product rule of a differential operator, not plus, but we have here now minus F1 S acting on F2, B1, ... And then, in order to act on B1, we have to anti-commute it past F1 and F2, which is minus is a plus. So we obtain a plus F1, F2, S acting on B1, dot, dot, dot. And this is how you can understand how S acts as an operator. As I have mentioned, S is nilpotent. S changes the so-called ghost number by +1. So we will later introduce the ghost fields, and the ghost field has ghost number 1, and the anti-ghost has ghost number -1, and S changes the ghost number by +1. S does not change power counting dimension. Which is important for renormalizability. So the further idea, as I've already said, and as I've announced when I discussed the Faddeev-Popov approach, are ghost fields. So a further idea, what we need in our BRST formalism is that we are introducing further idea. We will now be introducing ghost fields. Introduce so-called ghost fields, sometimes also called Faddeev-Popov ghosts, CA of X. And here we have use the notation that Dominik introduced last lecture. C is of course CA, TA, where TA are the generators of our Lie group. And CA is you basically have to kind of understand this as a matrix valued object. But I think you already are familiar with these notations from last lecture. So the ghost fields are scalars, however they anti-commute and follow or are fermionic. In other words, they violate the spin statistics theorem. So they are fermionic. As I've said, they have ghost number +1 and they have dimension 0. And the core idea, which I will be writing down on the other blackboard, but I already teaser it. So the core idea of BRST transformations is that for normal fields, we just take our gauge transformations. However, we change or substitute the gauge parameter theta by lambda c. So in lambda is this fermionic parameter, and c is our ghost field. So in other words, for normal fields phi, we have, which we know from last lecture, gauge transformations. And in these gauge transformations, we replace the gauge parameter theta. And please recall, Dominik first wrote theta, and then he later introduced theta bar. And one had the gauge coupling absorbed and the other not. And I am referring here to theta bar from last lecture. And theta bar basically then goes to lambda c a of x. This is basically the main idea. And we will then now write down the BRST transformations. Yeah.
The last line that you wrote in front of the phi, is it an integral gauge or S gauge?
Ah, no, it's delta gauge, sorry. It's it is meant to be an infinitesimal gauge transformation. So if you write a gauge transformation as phi goes to phi plus delta phi, this is the delta phi. That is what I meant with, and the index is just referring to the fact that I mean a gauge transformation. So let us come to BRST transformations, finally. Which, as I've said, will basically then
أعتقد أنه الجوست بارتيكل هذه تفسر كلامي الذي شرحته قبل قليل. فسنتابع هذه الجوست بارتيكلز والأنتي جوست بارتيكل نمبر التي تأخذ نمبر 1 وماينس 1 بلس 1 وماينس 1. سنتابع هذا الأمر.
Supersede our gauge transformations, and let me maybe comment on what we will be doing here. I will be just writing down the BRST transformations, and I will drop them from the sky, and you will see that they look like gauge transformations just with gauge parameter replaced by lambda c. And we will also get new transformations for, of course, the ghost fields. And all of them have one thing in common: they need to be such that the operator S is nilpotent. So basically, that we act with the S operator twice on a field, it gets zero, it becomes zero. However, you can also do a more general ansatz, which we will be doing in the exercises, and I don't want to spoil your fun in the exercises. So in the exercises, you can see that you can write down a more general ansatz, and then you just demand nilpotency, and in the end you see that your objects in your general ansatz, they have to fulfill certain requirements, and you can identify them to be structure constants or generators of your Lie group. And if you then go to a SUN gauge group, you see that you will exactly obtain the same BRST transformations as I will now be writing down. But as I've said, that is up to you in the exercises, and I don't want to spoil your fun with that. So step 1 is basically for our new field, the ghost field. And we would like to see what does the operator S if we act on the ghost. And what it does is basically gives us minus I g c squared, or if we write it down in component wise, we get plus 1 over 2 g f a b c c b c c, and these f a b c's are the structure constants of our Lie group. And maybe one nice thing is what you are wondering about is here it says c squared, and I said that c is a fermionic ghost field. Why is c squared not 0? Because c is still basically a sum of CA, TA, and the TAs are, for instance, in SUN matrices. So you have to basically view this as CA, TA, CB, TB. And if you then evaluate that out and look at it component-wise, you see that you get this expression. Let's check nilpotency, which means if we act with S squared on C, or in other words, we act with S on SC, we obtain minus I G. We obtain minus IGC squared from the first S and act on it with the second S. The S acts on the first C, which means SC, C. And then, because we basically now follow the rule for our fermionic differential operator. We have to commute, anti-commute S past the first C, which basically gives us an additional minus, which makes a plus out of this minus. So we get plus IG C SC, and we see that this is 0, so it is indeed nilpotent. Let us come to, that is already step 1. Step 2. And let us consider now the interesting fields, namely our normal fields, which are the matter field, the fermion, Q, and our gauge field, A mu. And as I've said, these will now be familiar to you because the BRST transformations of these fields will just be the gauge transformations. So in other words, BRST transformations for normal fields are like gauge transformations, but with theta bar replaced by lambda CA, and we obtain SQ, so S acting on our fermionic field is minus G CQ, where C is of course again CA TA, and SA mu is partial derivative of the ghost, d mu C minus IG, the commutator of C with the gauge field A mu. And let me also write that down in component-wise. Component-wise, this thing means S mu A is d mu CA plus G FABC CB AC mu. And as you can see, these are basically the gauge transformations of our fields. The TAs are the group generators, and the FABCs are the structure constants of our gauge group. We would, of course, again, let me write that down here. If you know, which you can do in the exercises, act on S again, you see that S squared Q is 0, and the same is true for S squared A mu. So of course, again, S is indeed, the transformations are such that the S operator is indeed nilpotent. Step 3 is now an interesting step again. I call it the BRST doublet because we have to introduce 2 new fields. So basically, as I've mentioned several times, and as of course is our goal, is I said we want to replace our gauge transformations with the BRST transformations. So we want our theory to be BRST invariant. So our Lagrangian needs to be annihilated by the S operator. And we have 2 options to do that. The trivial option is basically to write a Lagrangian as a BRST exact term. So some object S times some object X. And of course, if we then act with another S on it, it's trivially 0 because of nilpotency. And there is another possibility, namely that we write it down as an object which lies in the BRST cohomology, so it is in the kernel of Q, which means it gets annihilated by Q, which we want. However, it is not representable as a BRST exact object. And these are basically the two options that we have. And it will turn out that our gauge fixing and ghost Lagrangian will be written as a BRST exact object, so it will be the first option. And our physical Lagrangian, as I've said, is of course in the BRST cohomology, so it's the second option. And let me write that down, and then we will see why we need two new fields. So requirement for BRST invariance is that S annihilates the Lagrangian. We have two options. First, we write L as a BRST exact object. This is, of course, the trivial possibility due to the fact that S is nilpotent. And second, and this is then our physical Lagrangian, so it basically contains our matter field and our gauge field, is gauge invariant. And this is not representable as S acting on X, so not representable as a BRST exact object. And this will be the physical content of our theory. And now we wish to have a BRST invariant L, which contains a gauge fixing in the form S acting on X. Gauge fixing in the form S acting on X. And for this, we need two new fields, the anti-ghost field and the Nakanishi-Lautrup field, which is this auxiliary B field, which you have probably already seen in QFT 1b. Anti-ghost C bar A, which is fermionic, ghost number -1 and dimension 2. As you might wonder, C bar is not the corresponding antiparticle of the ghost C. So C and C bar are independent, which you can also see from the fact that C bar has dimension 2 and C has dimension 0. And the Nakanishi-Lautrup field or auxiliary field BA, which is bosonic, has ghost number 0 and dimension 2. And this B field is of course not propagating, so it's not a dynamical field. It doesn't have derivatives in the Lagrangian. And in other words, we can integrate it out using its equations of motion. So S acting on C bar the BRST, let's come to the BRST transformations of these two fields. S acting on C bar is BA, and S acting on BA is just 0. In here we can again see the nilpotency of S, which is quite trivial, because if we act once more with S on CA bar, we basically act on CB, we basically act with S on B, which is 0. And if we act twice on S, with S on B, it is of course still 0. So again, we have a nilpotent. We can ensure that our operator is nilpotent using these transformations. Let me now summarize the BRST transformations, give you some comments, and then we will be already going to the ghost and gauge fixing Lagrangian. Summary. And consequences. So our BRST transformations are given by delta A mu is lambda S A mu is basically, which we can still see here, lambda acting the partial derivative d mu c minus ig lambda, the commutator of c with a mu. And don't forget, lambda is our fermionic parameter, which we I erased it already, but which I've introduced a little bit ago. The BRST transformation of the matter field is given by lambda SQ, and SQ was given here, so it is basically minus IG lambda CQ. The BRST transformation of the ghost is given by lambda SC, which is minus IG lambda C squared. And the BRST transformation of the anti-ghost is lambda S C bar is lambda B, and of the B field is lambda S B is just 0. These are the BRST transformations, and now to give you some comments on them. BRST transformations are substitution for the gauge transformations. Which you can see here in the case of the gauge field and the quark, or the fermion. In other words, let me picture it like this: SQ and SA mu representations gauge transformations with the gauge parameter theta bar replaced by lambda c okay. The ghost field SCA basically, as you see still above in step 1, contains the structure constants. So it provides us group information. So let me picture it like this. Structure of gauge group. And we of course still have our nilpotency. S squared is 0. So far so good for the BRST transformations. Let us now turn our attention to the next, yeah.
So these S operators, they are no longer a representation of any specific group as before?
No, so basically this S operator, we introduced it, and it is there to generate symmetry transformations. These are the BRST symmetry transformations. And as you know from first quantum field theory lectures, if you quantize that and then consider the corresponding Noether charge of this symmetry transformation, this case will be the Q operator. And this is the BRST operator, but it has nothing to do with our gauge groups.
And has it to do with some other BRST symmetry group, or is that just this symmetry used in the sense of this transformation, but there's no looping behind?
Good question. As far as I know, it's basically just there to generate the BRST transformations. If you find, maybe you can do this as a homework, look out whether you can find some hidden group structure, but there might be some mathematical structures lying beyond this, but this is not of interest for our course here. So yeah, but as I said, so far it's just important that this S operator generates these BRST symmetry transformations, and once you consider the corresponding Noether charge of these symmetry transformation, you see that this Noether charge is basically the BRST operator Q that I introduced at the beginning of the lecture. So let us come to the gauge fixing and ghost Lagrangian, which will be our additional ingredient. And last lecture, Dominic introduced already the gauge invariant Lagrangian, and this will be basically now the second ingredient that we need for our theory. So the idea is, of course, that the gauge fixing can be BRST invariant, which is of course in contrast to gauge invariance. So of course a gauge fixing cannot be gauge invariant, otherwise it would not be a gauge fixing. But now the idea is that our gauge fixing can be BRST invariant, and our ansatz for this is a gauge fixing ghost Lagrangian, as I've already announced above. Is we want to write it as a BRST exact object, and let us more precisely write it as S CA bar FA. Obviously, this is obviously BRST, annihilated by the BRST operator or by this S operator. As it is just an BRST exact object. And let us make a choice. And for instance, we will later see why this is a good choice. Use FA as a gauge fixing to be xi over 2, BA plus d mu A. And plug this now in the Lagrangian and evaluate it. So let us evaluate this. Evaluate L fixed ghost is S of CA bar psi by over 2 BA plus d mu A mu A. If you are now acting with the BRST, with the S operator, taking into account that you have to anti-commute it past the C bar, because C bar is a fermionic object and S is a fermionic differential operator, you obtain BA psi over 2 BA plus d mu A minus CA bar d mu S acting on A mu. So I have not written down this, but as you know how the BRST action of the transformation, or basically the action of S acting on the gauge field looks like, you can plug it in yourself. And now, as I've said, this B is just auxiliary field, does not have derivatives, no independent dynamics, so we can integrate it out using its equations of motion. So we use the equations of motion for B, which are BA is minus 1 over xi d mu A mu, and we obtain for our gauge fixing, I now split the Lagrangian L fix ghost into the gauge fixing part and the ghost part. The gauge fixing part is minus 1 over 2 xi derivative of A squared, which should be familiar to you because this is the standard arc-C gauge that we have already seen several times. So it's the standard gauge fixing. And we have a ghost part. And our ghost Lagrangian looks like CA bar d mu acting on d mu CA plus GFA BC CB A mu. And that's basically already it. Let me conclude a bit and write some things about this, and then finally in the end, last 10 minutes, we will consider some Feynman rules for our new Lagrangian. So, conclusion. The Lagrangian has now the form L is equal to L gauge invariant, which is the Lagrangian that Dominic showed you last week, plus our new Lagrangian L fix ghost, which contains the phi df Popov ghosts and the gauge fixing. Obviously, this thing is the theory defined by this Lagrangian is BRST invariant, as we have basically done so, as we have constructed it. So it's BRST invariant by construction. BRST invariant. It contains the gauge fixing and the ghosts. And thus we can quantize it. So the theory can be quantized in the sense of the path integral from chapter 1. As I've announced, the Lagrangian now has exactly the form that we need for the path integral quantization. It contains this gauge fixing, and it can be quantized by the means of the path integral. And so basically these things are already obvious from what we know. What is kind of an outlook are that what we just did leads indeed to the Beer's T operator Q as the Noether charge. So we have not directly shown this, but you can do this. Leads to Q and to physically meaningful results. And you obtain Q as the corresponding Noether charge. And the theory is renormalizable, which we have not proven, but I think we will discuss this in future lectures. And basically doing all this work now leads us to the question, how do Feynman rules for our theory look like if we basically have this Lagrangian? And we have 7 minutes left, so enough time for discussing the Feynman rules. Yeah?
Maybe a question before that. So we had the different terms now for the Lagrangian. We started with L fix, comma ghost.
Yeah.
Then we have L fix and L ghost.
Yeah, L fix and L ghost are just, if you sum them, you end up with L fix ghost. So basically, L fix ghost is L fix plus L ghost. So I actually write it down as one Lagrangian because this is the new ingredient. However, here I wanted to split them in order to make you see that if we choose this gauge fixing for FA, then we basically obtain the standard AXI gauge that you already know from QFT1B.
At the point where we use the equation of motion for
Yeah.
so that means that we already had this fixed ghost term in mind. Do the Euler-Lagrange equation, we get the equation for B?
Yeah, if we have this, if we basically this B field does not show up anywhere else in the Lagrangian, only in the gauge fixing ghost Lagrangian. So if we just use the Euler-Lagrange equations, and in order to get the equations of motions for B, we obtain this because B doesn't have any derivatives, so it's just such a constraint equation, and then we can plug this solution for BA inside the gauge fixing and ghost Lagrangian, and then obtain exactly these two results for our gauge fixing and ghost Lagrangian.
So in our final Lagrangian, we don't have B.
No, not anymore. B eliminate. I mean, we can write down the final Lagrangian with B, but we can also eliminate it. And the final Lagrangian is then basically L gauge invariant plus L fix plus L ghost. I will also write that down now for the Feynman rules again.
And why do we need
Yeah, it's basically this constraint variable. Maybe because we are a bit running out of time, if you can go back to QFT1b where we discussed this, these constraints, and basically this B field is an auxiliary field which is just there to somehow almost like a Lagrange multiplier in order to make sure that these constraints are realized. And then we can, of course, integrate them out and get rid of these B fields. And of course, the B field is also somewhat necessary because we have introduced this as part of the BRST doublet together with the anti-ghost field. If you remember the BRST transformation of the anti-ghost, it is basically the B field. And if we already integrated it out, it would be kind of strange because then there would no... I mean, you could then write the BRST transformation of the anti-ghost in terms, which was just BA, in terms of this, but yeah, we don't do it at this stage. We integrate it out then on a later stage. Did you have a question?
Maybe later.
Okay, then let's come to the Feynman rules. Which is a new chapter, and because I knew it would be a bit confusing, I will write down the full Lagrangian once again, this time as L gauge inf plus L fixed ghost, and it basically is 1 over 4 f mu nu a, f mu nu a, plus q I bar times I d slash minus m. And this is, of course, to be understood as some kind of a matrix, ij, qj, and these q's are color multiplets. I mean, if you consider, of course, QCD, they are color multiplets, and in some other case, they are just multiplets. Minus 1 over 2c, a mu squared, minus c bar a, d mu minus G F A B C C C, and with our covariant derivative capital D is d mu plus I G T A A mu. Please mind the convention. Some authors write minus, and Dominic usually writes plus. And in the end, if you do it consistently, you get physically equivalent results, of course. But at the level of Lagrangian or Feynman rules, this might sometimes be confusing. And what we also do is let us integrate by part, because you have to consider this Lagrangian to be part of the action, and in the action you are integrating over the four-dimensional space-time. So you can integrate by part the ghost term, and because I would like to shift this derivative, which acts on all of this on the left side, I would like to shift it in order to be acting on just the anti-ghost. So integrate by part, I call it the ghost term, and after integrating by part, we get plus derivative acting on C A bar and only on C A bar, delta AC d mu minus G F A B C A B mu C C, and clean the blackboard the last time. I think in the standard model lecture, you already learned how F mu nu A in a SUN theory looks like, because you not only have the gauge kinetic term, but you also have the triple gauge boson and the quartic gauge boson interaction terms inside this F mu nu A. And I think have you seen that? Oh, okay, we have -1 minute left. Enough time for doing this. I hope you don't mind if we go a bit over time. Let me just look at the microphone. Yeah, everything should still work, right? Okay. So please let me do it properly. So the gauge boson term. Gauge boson term -1/4 F mu nu A squared. I write it down now like this, but you know what I mean. So we won't have time to do it step by step. I write down the result, and I hope that because I can remember that I think in the standard model lecture you at least wrote down how F mu nu A looks like, and then of course if you square it you have to do some algebraic manipulations, and then you obtain the result that I will now be writing down. So -1/4 d mu A nu A minus d nu A mu A squared. I think this should not be too surprising. This is the gauge kinetic term, and this is basically what you know from QED as well. And then you have plus G FABC, partial derivative acting on A mu A, A mu B, A nu C. This is basically the triple gluon vertex or triple gluon interaction term. Or if you don't consider QCD, it's the triple gauge boson interaction term. -1/4 G squared FABC FADE A mu B A nu C A D mu A E nu. So please, if you really want to calculate it yourself, remember that the field strength tensor was defined as the commutator of the covariant derivative d mu with the covariant derivative d nu and some prefactor. The covariant derivative is given here. If you perform this commutator, you see that you have a commutator of TA, TB then. You obtain, of course, the structure constants, and if you then you obtain F mu nu A, and if you then square it and multiply with -1/4, you will, after some algebraic manipulations, will obtain this result, so you can do this as a homework. And now that we saw the full Lagrangian, and we know that we have a gauge fixing, so quantization is possible, propagators do exist, we can now come finally to the Feynman roots. Let us start with the propagators. And we start with the gauge boson propagator. So basically, the term that is relevant is this are the bilinear terms in A. So this is this gauge kinetic term, and of course also the gauge fixing term, and gives rise to this propagator. Then we go to the fermions. Q bar I, Qj. This is the just the standard fermion propagator. Nothing too special. And the final propagator that we would like to consider here is the ghost propagator. Usually, sometimes the ghost propagator is with dotted lines, but this is difficult to draw, so I do it with these lines. Um, 5 minutes. Okay, we have to hurry up. The ghost propagator basically looks like a scalar propagator. And now let's come to the vertices. Actually, I wanted to do this a bit more extensive, but
طبعا كل هذه الأشياء إن شاء الله سأدونها في كتابي، ويجب أن أشرحها بالتفاصيل وبناء على نظريتي. هي طبعا مهمة صعبة، لكن ما دام وصل إلى فهم الرولز فهذا يعني استطاع أن يربطها بالعالم الواقعي. يعني احنا رأينا كل الاشتقاقات الرياضية التي تمت هنا عبارة عن جوست، أنتي جوست، أوكسيلاري، يعني أشياء كده الواحد يحس أنها ليس لها ارتباط بالواقع أبدا. ونحن نعلم أن معادلة ياغميل معادلة صحيحة ولها نتائج تجريبية، وأيضا فسرت QCD وفسرت QED، إذا لها ارتباط بالواقع، لها ارتباط قوي جدا بالواقع. لكن هذه مشكلة، أو هذا هو الأمر بالنسبة مع الفيزياء والرياضيات، أنك تدخل نفسك في استنتاجات واستدلالات وخطوات منطقية رياضية، ثم بعد ذلك تفسرها فيزيائيا. فما سنفعله هو بإذن الله تعالى سأخصص بابا، إذا ربنا جعل لي الفهم العميق لهذه المحاضرة تحديدا، سأخصص لها بابا وأشرح فيه هذه معادلة اللاجرانج هذه، وأشرح فيه جميع المكونات لها. بعد ذلك آتي لفهم الرولز وأحاول أن أشرحها. فور انتهائي بإذن الله تعالى سأنشر الكتاب مباشرة، وبعد ذلك نرجو من الله التوفيق والسداد. لكن بالنسبة لي حتى الآن إنه أرى أن الأمور عبارة عن طلاسم، وهي معقدة جدا جدا، لكن ستتضح الرؤية إن شاء الله في الأيام القادمة. يعني أنا كنت أظن هذه المحاضرة أنا أتحدث فيها أكثر مما يتحدث المحاضر في هذه المحاضرة، وكنت واضع لها زمن أكبر، لأنه أنا مفعم ويعني متفائل جدا بمعادلة ياغميل، أنها تقدم أقصى اتفاق مع نظريتي، والدليل على ذلك المحاضرة السابقة، حيث أنها كانت يعني مليئة بالمعلومات لدرجة أنني أنشأت وفكرت وبدأت في كتابة كتاب الحلقة 55. لكن هذه المحاضرة شوية صعبة، لكن إن شاء الله سنبينها إن شاء الله في الكتاب، وإذا فهمتها فهم عميق سأفرد لها فيديو خاص. هذه المحاضرة غير هذا الفيديو، يعني فيديو خاص أشرح فيه الحدود بناء على نظريتي، ليس بناء على الاستنتاجات التي وصل لها العلماء الذين اشتقوا هذه المعادلات، لكن بناء على نظريتي. نظريتي سهلة جدا. نظريتي الدالة هي عبارة عن دالة في 3 أشياء: كتلة، نسبة وقطر، كتلتين ونسبة وقطر. هي بس. وشوف هذه المعادلة دالة في كم متغير، كميات ضخمة متغير. فأنا ما سأفعله هو أن أدمج هذه المتغيرات الكثيرة في هذه المتغيرات ال3 فقط. هذه المتغيرات ال3. فهذه طريقة صعبة، لكن إن شاء الله يعني نسأل الله التوفيق والسداد.
5 minutes are left, so we have to do it a bit faster. Of course, something that is new is the triple gluon vertex or the triple gauge boson vertex, which is not there in QED because you don't have photon self interactions. Here, however, you have them. Basically, how you derive this is, of course, you get a factor of I by the Gell-Mann-Low formula. Then if you choose every momentum to be incoming, which we did, you get a minus I p mu for every partial derivative, which you have here, after going to momentum space. And then what you also do is you basically perform 3 functional derivatives with respect to these A fields. And you obtain then the following result: minus G F A B C this result. And maybe what you can do to be a little bit faster or to memorize the result, because you don't want to derive it every time, you can maybe start here at AC rho and go clockwise to AA mu. Then you are at rho and mu. So you basically end up with the G rho mu term. You basically see that you have the 2 momenta incoming. So you have the difference of the 2 momenta PC minus PA, and the only Lorentz index which is left is the new one, so the new. So basically you have exactly this term, and the other 3 terms you get by cyclic permutation if you just go clockwise. And that's basically the only difficult thing is then to remember the prefactor, and that's how you could remember the triple gluon vertex. The quartic gluon vertex, the gauge boson fermion vertex, and the new gauge boson ghost vertex are still left, but I think we have to do it another time, maybe today in the exercise. Okay. Let's shortly continue the lecture from today's morning, as we have not completely finished the lecture. I will just gauge boson.
سأصور هذه الشاشة.
Fermion vertex and the new gauge boson ghost vertex are still, and that's basically the only difficult thing. 3 terms you get by cyclic permutation if you just go clockwise, and that's basically the only difficult thing is then to remember the prefactor, And that's how you could remember the triple Gluon vertex. The quartic have not completely finished the lecture. I will just finish the section about Feynman rules, and then we will transition to the exercise. So already in the lecture this morning, we discussed the triple gauge boson interaction vertex. I've just written down again the corresponding term of the Lagrangian and the corresponding Feynman rule. I also already explained how to derive this Feynman rule. Let us now come very quickly to the quartic gauge boson interaction vertex. And let me just write it down. The derivation is analogous to the triple gluon interaction vertex. You just need then 4 functional derivatives with respect to these 4 fields. And it's with respect to the functional derivatives a little bit more tedious. However, you don't have any derivatives in the corresponding terms, so you don't have momenta showing up. We have minus I g squared f a b e f c d e g mu rho g mu sigma minus g mu sigma g mu rho f a c e f b d e g mu nu g rho sigma minus g mu sigma g mu rho plus f a d e f b c e g mu nu g rho sigma minus g mu rho g mu sigma. This is the Feynman rule for the quartic and gauge boson interaction term, and which is now new for you because in QFT 1b we only discussed quantum electrodynamics, and in a general non-abelian Yang-Mills theory, of course, we have gauge boson self-interactions, which are these triple and quartic gauge boson interaction vertices. And yeah, this is basically something new and is not there in QED, which is of course good, because if it would be there in QED, we could not properly see as photons would interact with themselves. So therefore it's actually nice that nature decided like this. So then let's come to the fermion interaction vertex, which is also present in QED. I have written down already the corresponding term in the Lagrangian. And this should be quite familiar to you. The only new thing is that we now have this generator TA showing up in this Feynman rule, but it's basically the same structure as in QED. Now a new, also very new interaction vertex is the ghost vertex. Here is the corresponding term in the Lagrangian. let me write down the Feynman rule. So I choose the momentum of the ghost to flow inwards with P, and the anti-ghost momentum K to be outflowing, and the gauge boson momentum Q to be inflowing. And the vertex is given by G, F, A, B, C, K mu. So basically, just consider we get a factor of I from the Gell-Mann-Low formula. We get this G, F, A, B, C and the minus, and then we get for the this time outgoing momentum I P mu, and I times I is minus 1, and minus times minus is plus. So therefore we get G, F, A, B, C, K mu as a vertex, as the Feynman rule for this vertex. This is also not present in QED, obviously. Similar to the gauge boson self-interactions. And now let me just close this chapter about Feynman rules with some remarks. So first of all, as I've said, the ghosts can now interact. They can participate in the interaction, so they can appear as internal lines in our processes. Ghosts interact. Can appear as internal lines in our Feynman rules. And this is obviously not the case in QED. In QED, the ghosts completely decouple from the theory, so we need to not to consider them in any processes. As I've already said, C and C bar, so C bar is not the associated antiparticle of C. C and C bar behave differently. Why do I say this? If you have a look here, we see that C bar and its corresponding momentum K is somewhat singled out, because I mean, we will compare this now to a similar interaction vertex of a gauge boson with two scalar fields. I mean, they see the difference. So behave differently. C bar and associated momentum K singled out. And we see, therefore, that this vertex is not gauge invariant. And to see this, let us compare to scalar gauge boson interaction. Of course, if we introduced a scalar field to our theory, we would have two interaction vertices, two scalar fields with two gauge bosons, and one gauge boson with two scalar fields. I will just consider the triple vertex with one because I want to compare it with this one. Scalar gauge boson interaction. So this time I would like to choose every momentum to flow inwards. P, K, Q, A, B mu, phi I, phi j. and this vertex is then given by minus ig p minus k mu t a I j. And as we can see, none of the fields is in some sense, or one of these momenta is singled out. So both momenta participate in this vertex. This vertex satisfies the Ward identity. Satisfies the Ward identity, so it is gauge invariant. If we consider a contraction with the gluon momentum or gauge boson momentum, which is, according to momentum conservation, minus p plus k mu, we see that we get something like p minus k mu, p plus k mu is p squared minus k squared, is, if we set it on a mass shell, 0. So it satisfies the normal vertex, let's call it normal in quotation marks, which I mean the vertex with gauge boson and two scalar fields, satisfies a Ward identity. In contrast, the ghost vertex, as I've said, does not satisfy this Ward identity. Which means that it explicitly violates gauge invariance relations like the Ward identity. So this is the end of the lecture and the end of today's lecture and the end of the chapter about Feynman rules. So thank you for your attention.
طيب شفنا المحاضرة وعبارة عن مجموعة من الطلاسم ومحتاجين نفكك حدودها حدا كما قلت أن سأحاول أن أدون في كتابي ما فهمته منها بإذن الله تعالى. عموما ربما نحتاج إلى المحاضرة الثانية سأراها سأطلع عليها إذا كانت فيها شرح أوفى، هذا سيفيدني في كتابي بالتأكيد، وأسأل الله يكون فيها شرح أوفى لأنه سيفيدني كثير، وإلا سأكون مضطر أن أناقش هذه الحدود بما فهمته، وربما ستكون عندي مشكلة في أنه هناك كميات من الحدود مطروحة والمجموعة، وهذه الحدود يجب أن تفسر بطريقة أو بأخرى. ربنا يسهل إن شاء الله. السلام عليكم ورحمة الله.